stragglers. Welcome, everyone. Hello, my name's Danielle. Full disclosure, I didn't think I was nervous, but then while I was waiting to speak, I realized I lost my backpack. So if anyone finds it, please just leave it where it is. I will come get it later. So like I was introduced, I'm Danielle Adams. I'm coming here from New York, and we're going to be talking about high-profile failures. So a little bit about me first. I work at Heroku. I'm the Node.js language owner over there. So that means I maintain the build pack, and I'm responsible for all of the users' builds and runtime environments on Node. But we're not going to be talking about Node today. We're actually going to be talking about security. The reason I'm up here is because I work during the day, but then I also, at nighttime, I'm a student at a university in New York where I'm studying cybersecurity. And as I've been doing this, I've realized that, so it's been about a year and a half now, and I've realized that as I'm learning more about security and information security and application security, I realize that it's actually making me a better developer. So even if I end my program and I decide I hate security, I don't want to do this, it's definitely made me think about software development a little bit differently. So that's what we're going to talk about, learning from high-profile failures. What can we learn from all of these big hacks that have happened, big hacks, small hacks, and how we can use them to make our software development process a little bit better? Or what I would just like to call it my favorite hacks, things that seem to have gone so wrong, but they have happened from such simple issues. So before we get started, I think we need to get some of the terminology down. Oh, there's a bunch of people coming in. Hey, everyone. Okay, so some of the terminology. So cybersecurity. When people think about cybersecurity, there's a common misconception that it is the practice of trying to keep people out. And that's not the case at all. What you're trying to do is make it so hard and so tedious to break into other people's software, into their servers, into their databases, that it's too costly, it's too time-consuming, that they don't want to do it, and they just move on to the next easiest one. So a couple other terminologies that we want to keep in mind. So I'm going to be saying threat a lot. A threat is something that it can compromise the confidentiality, integrity, and availability of any sort of assets. Database would be an asset. CIA is a common kind of triple term that you'll hear when you're studying information security, and it's what we're really trying to protect. And then there's vulnerabilities. Vulnerabilities is a weakness in any infrastructure that makes it susceptible to a threat. So this doesn't just have to be a server or a database. This could be hardware. This could be a physical building. Anywhere where somebody can break in and access something they're not supposed to see. And then there's an attack. And so this is probably the most self-explanatory. An attack is an exploitation of a vulnerability in one way or another. So case number one, we're going to be going through real cases that have happened and how we can learn from them. So I'm going to call this Alice Agency. I'm not using any names because I'm not here to shame people or any companies. Everyone makes mistakes, and what we really want to take away from this is the lessons that we learned and not actually look at the details like names. So first of all, so in March 2017, there was a vulnerability in a Java web framework that was discovered and it was disclosed. It was an end-day vulnerability, and the vulnerability allowed remote code to execute when passed into content type, content disposition, and content length headers. So if you can imagine, you're making an HTTP request and you include executable code in one of those content headers. It means that the middleware or the web framework was not parsing these correctly, and it was allowing remote code to execute in these web servers of these Java apps. And it was an enterprise piece of software, which we'll talk about why that's important later. So what is an end-day vulnerability? So it's been disclosed to some sort of vulnerability database. And so this is the lesser known version. What's really popular is zero-day vulnerabilities, and those are the vulnerabilities. So there's two types. There's end-day and zero-day. Zero-day is a vulnerability that it hasn't been disclosed, but it's been discovered and it's been exploited in that moment, or on that day, which is why it's 0 day. And then end day is you're given the reason it's end day is because you have day 0 when it's been discovered, and then you have a couple days. There's a patch that might come out in 7 days, and then maybe in another 7 days you've issued a patch. And so of a study of 6,300 vulnerabilities, over 99% were end day. So it's a kind of a myth that 0 days are the scariest because they are the least common. Most common are end day vulnerabilities. They shouldn't be because they could be fixed by just making a patch, but the same study found that it takes an average of 30 days to fix a critical patch. So that means from the time that the vulnerability has been disclosed to the time that a patch is released to the time that it actually gets fixed, that's 30 days. That's a lot of damage that can happen in 30 days, and we will see why. So this is just a sample HTTP request to give everyone a visual. Using content length and content type is not an uncommon thing. This is a sample request headers from an Elixir server at Heroku. And just to make it bigger, this is what we would usually see for the values for these types of headers. And so when the vulnerability was first disclosed, this is what it was found, is that this is a screenshot from the server, from the researcher that had disclosed this. And so, go ahead. And so what they found was that they had these headers that they were able to put into this request, and then they were able to create a little line that just executed some code, and then they were able to see that execution in the server logs. So 6 months later, it was disclosed that this agency had 145.5 million people, their sensitive data had been accessed by an unauthorized party. And so the agency disclosed this. They disclosed it 6 months later. It had happened 4 months before, which means it happened 2 months after the vulnerability was disclosed. That's a full 60 days that they just didn't patch this. And it was not good. And so what we want to take away from this is that the confidentiality of the user had been breached, so kind of that term that I was talking about. And so when we are protecting data and we're protecting assets, confidentiality of data is really important. And so it was just completely exploited. And so, so how do we want to prevent this? So just to kind of switch gears for a little bit, so static analysis is a pretty common way to prevent security vulnerabilities. There's a lot of different types of static analysis, and I think that there's this misconception that just having any static analysis on a code base is just like automatically it's going to prevent regressions and it's going to prevent tests and make my code better. And it's important to understand the difference between all of these. And so for people that don't know, static analysis is running an analysis on code without actually having to execute it. So ESLint and TypeScript are both forms of this, ESLint being like a linter, and then TypeScript doing type checking. So when we're looking at static analysis for security applications, we want to make sure that, so this is a diagram that I stole from the OWASP website, which I will talk about what that is in a little bit later. But so we have this line in the middle, and so we see that the x-axis is false positive rate and the y-axis is true positive rate. And so we see high false positive and high true positive. That's usually, I would say that's where a lot of static analysis tools fall. Then we have tools that report vulnerabilities in the middle. We don't really want that. That could be flaky tests. False positive and true positive, we don't want anything like that. It's useless, just throw it away. But what we want is false positive to be down to 0 and true positive to be in the 100%. And that's where we want our static analysis for security tools to be. So that's the ideal vulnerability detection. And so a dependency scanner is a really good use case for this. It analyzes your source code. Dependencies are open source libraries that we use, and we don't necessarily we haven't written the code and we haven't looked at the code, and most likely we haven't really tested the code unless we've tested that it works. And so when we use a dependency scanner, that is, we can kind of see if it's vulnerable, just based on the databases that have for detection or for disclosures. So I really like Sneak. I think it's a good tool for NPM and anything in the Node ecosystem. I believe, I could be wrong about this, I believe that it was first built for Node projects, so front end, back end. And so what it does is it goes through all of your dependencies and it takes a scan at them and looks to see, matches those dependencies to see if there's any critical or medium or lower vulnerabilities, which is kind of how vulnerabilities are classified. Severe is the ones that you want to patch pretty quickly or have a schedule for. Low is, you can kind of get to that later, and especially if there isn't a path forward. And then it also, sorry, it's a little blurry, but there's also gives like a full description so you can really understand how to move forward with these vulnerabilities. So case number 2, I'm going to call it Bob & Co. Bob & Co. is a dating website, which, so we can all imagine how important privacy is, or confidentiality is in a dating website as well. And so it was hacked. And so in December of 2015, a data dump containing user data was found online and confirmed to belong to the site. I don't know how it got there, but that isn't really the important part. What happened afterwards is kind of the crazy part. So after the data dump was found, so the data dump being their database of user data, emails, hash passwords, some other values. And this didn't really matter because emails, anyone can make a fake account, like it could be inactive, whatever. So that was fine. But then a second dump was released. And it was the source code for the website and internal emails. And this is where it got really crazy. And so initially, like I said, it was a dump of the username and password, and the passwords were encrypted with BCrypt. And so BCrypt is a one-way hashing algorithm to use on password storage. And so it's by design very slow. So when it does perform, and you can make it even slower. So you can run it a few times, up to however many times, and the algorithm will be very slow to perform. And it's like that by design. And so when this dump was first revealed, it was decided that, people were like, we could see that it's using BCrypt. This is going to take a long time, but at least we're going to try. But then when the source code came out, so this is what a functionality, or this is what a kind of a diagram of what a password cracking program would look like. They're on the internet. You can look them up. And so all you have to do is, this is a common password cracking tactic where you take a dictionary list, and it's just you can find a list of the most common passwords. And it's just, my password, my dog Spike, like all of these words that people just use because they're not using secure passwords. And so what it does is it runs against the hash dump that's been found, and it'll look for matches, and so that it can see, this hash equals this hash from this plain text word. And so with BCrypt, that would have taken a long time because of the nature of because it was a CPU consuming and a time consuming hashing algorithm. And so when the source code came out, so we have this code, and this is the most interesting part. And just take a moment and look at this. Hopefully everyone in the back can see it too. And I just want to see if anyone recognizes what is kind of weird about this code. And that's your hint. So what's happening here is we have this first initial password value. We're running an encryption on it, which presumably is the BCrypt. Great. And then we get here. It takes the original plain text password, and then it runs another encryption value on it, or encryption algorithm on it, MD5, and then it assigns it to a login key. So we're taking what we've done to make this application secure, and we're completely sidestepping it by encrypting it with another encryption algorithm, and then storing that too. So what is the difference between MD5 and BCrypt? Well, they're both one-way hashing algorithms. MD5, once upon a time, it's better than plain text, we'll just put it that way. And so MD5, it outputs an 128-bit hash value, whereas BCrypt, the way that they knew it was BCrypt is that it starts with a $2 value, so they saw those in the dump. And so MD5 is fast to brute force and fast to, not really decrypting, to crack. And MD5, though, it would take days to run because it's less time consuming and it's less expensive in terms of CPU power. And BCrypt would have taken years. So what happened? So entire profiles of 37 million users were exposed on the internet, including names, emails, phone numbers, credit card numbers, purchase history, profile descriptions, weight, height, everything. So you could see who clearly the active users were and the inactive users were. This would not have happened if the second password hashing had not been created. I just want to make that clear. Confidentiality was imposed on, but most importantly, privacy of users was also breached. Next slide. And so just to make a distinction between confidentiality and privacy, confidentiality refers to data, whereas when we're talking about privacy, we're really talking about the person. And so everyone is entitled to privacy. If privacy is breached, that could lead to an endangerment of somebody's life, that can lead to them going through emotional turmoil. And so, you know, my credit card can go on the internet, but and that's a breach of confidentiality in terms of data. But if someone were to see my credit card history, that's a breach of my privacy, something that I would argue that I deserve. So prevention on this. So just looking at the source code, I see two stories here. And I don't know what happened. I wasn't there. I'm not going to pretend like I understand what happened this day. But what I will say is that I do see two kind of sides here. I see this password encryption, which was an effort to obviously keep the passwords and the user's privacy protected. And then I also see another story where someone decided that that was too slow, and they also wanted to make there might have been something with sessions, I don't know. And what they were doing is they were sidestepping probably the slowness of BCrypt and making it so that the password was available in case they wanted to maybe re-log in or whatever. And so this person was really looking at user experience, and this other person was wanting to make this application more secure. And they completely butted heads with each other. Neither made, no one really won in this scenario. Oh yeah, okay, so this is, see this and this. So this is easier said than done, but I just want to highlight that I think that there is oftentimes a kind of a separation between the development teams and security teams. Security engineers are there to break things, development teams build things, and so, but when the two, I don't want to say two sides, but when everyone collaborates, you do come out with a better product, and it still is your responsibility as developers to make sure that product is secure and it's also cool and awesome. So number 3 is, oops, oh yeah, that's fine. International Airlines, again, names are changed to defend the hacked. So in late 2018, there were reports of JavaScript assets that had been tampered with on this airline's desktop app and mobile app. So they were using, I assume, like a Cordova around their HTML and JavaScript and CSS to create a native app, I'm pretty sure. And so that's why the same JavaScript assets were being used on the website and in their mobile app. So this is the JavaScript that was found running on the page that may have or may not have been subject to exploiting a user's data. So did I skip something? No. Okay. So so let's look at this. This already looks shady here. It's wiping the entire payment form, and it's assigning it to a JavaScript object. And then what is it doing? It's sending a post request to some other random website, and as you could see, oh yeah, and that's important. So you could see it's even using HTTPS. So it wasn't just like a random site. These people took the time to, let's just assume that the domain looked very similar to the source domain. And then they also took the time to create, to get it, to register the domain with a certificate authority because it is using HTTPS. So an external analysis, and all of this, by the way, is very, this is all third-party like research. So a lot of these attacks that happen, the company's not going to talk about it, but researchers, they study and they look at what happened, and that's how we kind of learn. And so this one especially, since this one is actually pretty recent, external analysis of the code was conducted, and it was likely a stored cross-site scripting attack. The malicious code had been appended to one of the airline's JavaScript files, and that contained an open source library used for their own distribution. So if you can imagine, they had a library. For some reason, they had uploaded it to their own CDN. I don't know why. There's a couple of reasons why you would do that, and so someone had gained credentials to this other asset through their CDN, and then they had appended to the JavaScript file. So this other JavaScript was running, and it went completely undetected. So cross-site scripting, just to go through, it's number 7 on the top vulnerabilities released by the Open Web Application Security Project, OWASP. OWASP is an unbiased, kind of international non-for-profit organization that makes sure to create standards for web security across the internet. And so they have a top 10 every year. Cross-site scripting is always on it because it affects something like 2/3 of all browser applications, which is not a small number. And browsers don't have a secure default. So it's up to the developer to create a safe experience. So there's 3 types of cross-site scripting. The type that we saw was a stored cross-site scripting. There was something from the company server that had been injected with code, and then it had been returned to the client being the browser or the app, and run and executed. There's also reflective. The best way to describe this is JavaScript that has not been injected into the source code, but it has actually been executed from being kind of put into the browser by a third party. So using a phishing email to append query params to a URL and then opening that into another company's website where they know that they can run JavaScript through an input field or whatever. That would be an example of reflective. And then there's DOM-based. And so this one is lesser known, but this is manipulation of the DOM, not through reflective, not through stormed, and that will change the environment of the victim to do something that they don't want it to do. So 380,000 users, I shouldn't be laughing, had their personal and financial details stolen while booking and updating reservations during the span of 15 days. So this went 15 days where people were just going online, making reservations, checking their, I don't know, their status or whatever. 15 days, and all of their credit card information just swipe, send to a random person, and then that's it. So while it was a case of stolen data, the integrity of the website had also been compromised. So I wanted to highlight that as well because this was, because the website had been tampered with, and these are kind of assets of the company, the integrity of this website had been exploited. And so prevention of this. This was a specific case, first off, because what had likely happened was I think I said this before, was that somebody somehow got access to their own CDN. And so because where this code was coming from, it was an authorized JavaScript file that had been loaded from the company's CDN for whatever reason, and then it had been executed. But when I was looking at this, I was thinking, well, even if they had done that, shouldn't there have been some sort of policy where this origin website would not have been making calls to a third party? Because that's what core is. So cross-origin resource sharing, by default, actually, this is one of the better defaults of most browsers. This policy should have helped, and they shouldn't have been able to make the call. So that tells me that the company probably had some lax CORS policies, which would have made it easy. And the attacker probably saw that when they were making the call to, when they were kind of like looking at the website and figuring out, you know, what their next victim would be. They saw, hey, we can attack this because they have a pretty open CORS policy. Yeah, so using a CORS policy with a trusted whitelist, this probably would have helped that, and the client is adhering to the design principle of secure default. So there's a set of design principles, which I have no time to go into, but if you want to talk about afterwards, we can. And so this would be, what they have done is just kind of opened it up to everyone, and this would have been a secure default. And so this is what this looks like. Yeah, if I'm a source URL, or if I'm a source application and I load my website, I want to make sure, and I want to use a subdomain, or I want to authorize another website, maybe like a Google Analytics or something, to be able to send HTTP requests or AJAX requests from my browser, then you should do that through this. So using this principle of safe default, it's really important to understand what the browser and what the protocol, comes from HTTP, what you're really getting with these, because you can actually go pretty far with securing your websites, and having, just being open to the internet doesn't always serve your users best. And so just keeping up with what the browsers are offering in terms of security is actually really important too, because this is always changing and evolving. So really, what I'm hoping you're taking away from this is that there are a lot of big hacks that happen. Most of them are pretty simple. These aren't masterminds that these are happening to. As long as you're aware of what's going on with your software, easier said than done, I know, but there are little ways to do that. The more that you make it harder to actually break into your software and put your users at risk. And so using these failures as an opportunity to create better software is really what I'm hoping that you all will do. And that's all I have. Thank you.